Thanks a lot. I would say this has been a really interesting forum in which we have been sharing ideas. I'm actually taking some ideas to home to see if this can actually work at Belle II. But it's my turn to explain what we are doing there in this experiment with the hope that the discussion is actually useful and also for getting ideas from you about what we are doing. So let me start. At this point, I think Belle II has been already shown in multiple places. So you may be familiar already with the experiment, but this is just a snapshot of what we are doing. It's electron-positron collider that works at Upsilon forest resonance. So that's why it's called a B-factory, because we produce a lot of B mesons. All the readout has completely upgraded with respect to the previous B-factory Belle, and we are expecting around well, the output of the readout is around 30 kilohertz in the full luminosity. The software, I will talk a bit more about that in the next slides, and just to remark that we are using grid computing as other LHC experiments. Now, let's talk about the numbers. The interesting thing about Belle II is the integrated luminosity. We expect to produce around 15 per atom at the end. This is 50 times more than the previous B-factories. It's usually the number that we use to get our benchmarks. And just to say that the estimated size of the data set collected by the experiment is of the order of petabytes per year. So it's not as big as the high luminosity LHC. So that is not our challenge, but our challenge scales when you take into account the number of events that corresponds to the luminosity that we're expecting. So that's what represents a significant data management challenge. Now, our strategy to reduce the data is not about removing objects, because the size of the event in the reconstruction is already small. It's mostly about the scheming. But in order to talk about the scheming, I have to say a few things about the software. So this is our software framework. It's called BASF2. It's from Belle II analysis software framework, but this is more historical thing. But it does more things than just the analysis. It actually performs all the unpacking of raw data, tracking, clustering, and so on. It's an executable. It's a wrapper from Python 3 and controls the sequence in which these things called modules are executed. And these modules are just blocks of code that performs a specific task. It could be, for example, well, some part of the reconstruction, some triggering, etc. It contains C++ under the hood, and it exchanges data via this data store that is just a global accessible interface to the objects in the modules. And well, root is used for persistency, so our data formats are actually based on root. And the output it's basically content of the data store into T3s. And well, it's separated independently permanent and event durability events. So that's what the software does. And let's move on to the data formats directly. So as I mentioned previously, we have this thing that's called the mini data summary table. It's the output of the reconstruction, and as you can see, it's already quite small. So we are not dealing with the task of removing objects. However, we have still to deal with the number of events that people have to process. So this contains strictly objects that are necessary for analysis. So no raw data information is stored after the reconstruction. And the format that is for end user analysis is the UDST. So this is just user data summary table. It contains approximately 20 kilobytes per event. The reason why it's larger than this one is because we are performing the scheming of the events that are interesting for the analysis. But additionally, we include the objects that can be used for getting the results. That is just particle lists. This is just a list of objects that represent particles and contains information of each one of the candidates that are reconstructing the events. Okay, and yeah, this is just intended for the end user physics. The workflow is pretty standard in Belle II. We perform very similar things, going from the reconstruction to the MDST that I mentioned it, and I will focus later into this part that is maybe the relevant for the session. So this MDST, as I mentioned already, contains just the objects that are used for characterize particles on each event. So when you perform the scheming, you reconstruct actually these particle candidates, and then based on that, you select what are the events that are interesting for your physics case. And this is stored into this UDST. So after the scheming, including the information of the particle level data structure. So you get some gain into the CPU that will be used after all, because you don't have to pass through the process of reconstructing particle candidates again. But of course, there is a small cost in increasing the size that you will use in the disk. Now, this is the list of objects that are included in these MDST and UDST formats. It's pretty standard, so I will not go through all of them, just to say that we contain the information of the tracking, so tracks and fit results, vertexing, just to reconstruct V0 candidates like the shorts, lambdas, energy clusters, both from the electrocalorimeter and the KLM, that is the last layer that reconstructs muon KL long candidates. For particle identification, objects, that is mostly the likelihood of the different subdetectors for reconstructing particles, trigger information, and Monte Carlo, it's also stored for MC matching. And the interesting one probably for this talk is the particle candidates that are stored on the UDST. So this is as I mentioned, the collection of particle objects that if you want to go to the definition, you can click here, and this sends you to GitHub. And this is the definition of this particle list object that we use for performing the analysis on candidate base. Now, the physics program at Belle II, let me just say a few words about it because it's relevant for the discussion. We just don't do B physics, but there is quite a long list of analysis that are being performed right now. So this part is just what covers the B physics, the B physics in our program, but we also have charm, searches of new hadrons, exotics, dark sector, tau physics, and we can extend this if we have the capability of running in Upsilon 5s, 6s, or electroweak. And the important thing here is that each physics working group has its own, often unique analysis requirements. So that's when we start to deal with different different requirements that will be defined for the scheme. Now, let me talk about how the scheme is defined at Belle II. I think this is a pretty cool feature of the framework. And it's quite easy to do it, maybe too easy, and that's a problem. I will talk about that later. But the thing is that the analysts, or the working groups in this case, just define some metadata and then load the standard particle lists that are required to analyze the kind of events that you are interested with. Then applying some cuts into the particle list that you have just defined, like for example, in this case, it's just electrons, muons, and then apply the selection using this declarative format. And finally, reconstruct the output particle list that will be available in the UDST. And all this is just, also you can apply additional cuts into the particle list depending on what is the kind of things that you are interested. And that's it. So this is the definition. And then once it's done, you can put it in the repository, and then it will be processed on grid. It's super easy, I would say. And just you have to fulfill some requirements on retention rate, memory usage that are defined by the managers. Is mostly depending on the limitations of the sites. So the scheme is that once you have the definitions, this is centrally produced by these production schemes that produce the UDST. And the idea is that the analysts use the grid to access this UDST format to get the n tuples and then get the final result. So the framework itself, I think, works great. The problem is when we move towards the scalability of this thing, and that's when the problems start. That is probably where we would like to get some ideas. All right, so this is the process of data reduction. Again, very similar to what has been shown already. One of the first problems that we have seen is that the analysis schemes runs on all data events every reprocess campaign. So this represents considerable delay for analysts. In particular, since we are ramping up the luminosity, people want to analyze data now, but this is sometimes not possible. So many of them are actually analyzing into the non-scheme stream, which is, let's say, okay-ish right now, but as we increase the luminosity, this will not be possible anymore. One idea is that we also have defined at the HLT level some schemes that in principle are intended for calibration. Some people can actually use these ones for performing analysis. So the scheming can in principle be done, could be done, for example, in this one, HLT hadron, that is basically trying to identify hadrons in the event. But this is not suitable for all physics groups. It's just a partial solution. And one of the big problems is that not all analyses are suitable for a scheme definition. They present very high retention rates. Thanks. So if, for example, you are trying to find, I don't know, a bump coming from 2 tracks into your band, then we are pretty much making a copy of the full data set. Well, once the scheme package gets the output of the different requirements of the physics groups, in principle, they must be analyzing this part. Plus, we have what is called the performance scheme, and this, in principle, must run faster. They actually come from this stream of already HLT, well, high-level trigger scheming. And the idea is that these files must be faster available because that's the ones that are intended for getting the performance, the systematics, and they must be in place by the time that the data actually comes here. So the final goal is plugging this into machinery that automatically gets most of the systematics. Well, the activity on the grid, just to mention that the scheming does not represent an impact into the CPU usage. It's mostly heavy I/O operations. And as I mentioned it already, one of the big problems is the delay of the production of the scheme, given the data, these heavy I/O operations. And another problem that was already mentioned in Atlas, and it actually triggered an alarm on my head, is that we have 70, 80 individual schemes defined. It's just by the requirements of the groups. As I say, defining a scheme is quite easy. Then we don't know really if we. I mean, the idea would be to reduce this and data popularity in Rusio. Now Rusio is used as a distributed data management system. So the popularity in Russia will provide answers if all of them are actually being used or not. And if not, so just have a word with these groups like, hey, but you define a scheme you are not using, what's going on? And well, the analysis with non-scheme data put heavy load on the grid services. So right now the scale is okay, as I said, but as we increase the luminosity, this will become more and more a problem. So we have to solve this eventually. And finally, I would like to say a few words about the long-term implications for data preservation. So when you take the numbers, at the end of the Belle II experiment, we expect around 40 petabytes of scheme data, plus similar size of Monte Carlo that must be preserved. This is more or less an order of magnitude larger than the previous experiments that we have been comparing with, so CDF, the zero bar, and of course, multiple copies should be preserved to avoid data loss from hardware failure. So this is relevant because, well, we had a reminder a few days ago about why this is important to have access to what you would call legacy data. And I think it's a relevant topic to discuss. And since this is an excellent forum to do it, so we must ensure that analysts may pursue any scheme, any analysis that is not covered by a scheme. That's more or less in our current situation. That data processing require of operative central services like conditions database that are needed to correctly interpret what are the objects located inside these formats of Belle II. So the analysis software framework depends on external libraries and several software packages, and the considerations must be made to ensure the usability of the software after the shutdown of the experiment. So we consider that broader discussions about the feasibility of the long-term data analysis would be valuable for the high-energy physics community, in particular identifying services that would benefit from common use by many experiments. So this would help a lot. So that sends to my summary. So the Belle II, as I mentioned, is a multi-purpose experiment. That it means that we have many requirements for the analysis, and we will collect 50 times more than the previous B-factories that scales the challenges that they had in the past. The reduced data formats are basically based on root, designed for reducing impact in the storage and in I/O operations. Well, the schemes are defined by each working group, already mentioned, and the analyst, the idea is that the analyst runs over the schemes without the need to recreate particle level information. I think this is a really nice feature. And the major challenge is how to deal with the current and future analysis that we don't have yet in mind that are not compatible with the scheming. So they're just because the retention rate is too high or the signal is not covered by any scheme definition. So that's it from my side. Thank you.
Thanks a lot. Other questions on Zoom?
I see. Okay.
I don't see any hands. So are there questions in the room?
There's one.
Mike Sokoloff. Page 3 has projections for integrated luminosity. I'm trying to understand whether that projected luminosity is, you've got your data on tape on the right, you've got projected luminosity on the left. At what point do you expect to accumulate 50 inverse Atabarns? And is that really 5 inverse Atabarns that you're talking about accumulating by 2027, or?
Yeah, that's
Because there's a big difference between 5 inverse Atabarns of data in the next 5 years and 50.
yeah, that's true. And actually, it depends on how the instantaneous luminosity can be increased. So the projections so far have been right now put officially until the 26th. And well, the goal of the 50 inverse Atabarns is still on the table, but it's probably beyond 2030. It's just a matter of how much you can increase the instantaneous luminosity. I don't know if Paul wants to comment about that.
Can comment a bit, but yeah, there's supposed to be an accelerator upgrade on that timescale, so just after the end of this fall. But the 50 inverse Atabarns is on a timescale of a decade or a bit more than that. It's challenging.
Are there more questions? Yeah.
Not a question, but a comment. Thanks a lot for mentioning the data preservation impact of the simplified data formats. You're probably aware of DPHEP and the activity between other experiments happening in that area. And I think we are looking for someone from Belle to contribute to this year's status update. So I can only invite you to contribute what you showed also to that.
Thanks a lot. Yeah, it will be very interesting. I'm just jumped into this kind of discussion. There is already a task force inside Belle II that is discussing this, and I just jump into this boat to discuss from the computing point of view, in particular in my case. But yeah, it would be great if we can have some activity together. Maybe not just me, but other people. So yeah, let's exchange the contact. Thanks.
More questions? I had one. You talked about these different schemes. Roughly how many are there?
Yeah, I mentioned that there are like 80 right now, 70, 80. So this change depending on the campaign. But the main question is how to reduce this number, because it sounds larger than what we maybe need. So the first step on this would be to finish the technical implementation of data popularity in our grid. That will give us the answer of, okay, what are the data sets that are being used in reality, and which ones have no access or no access at all, or just very small access. So just to understand the situation.
Okay, then thanks a lot, Michel.
Thanks.